Hello everyone, welcome you all back to Module 3 Part 2, that is Ventilation and Air Movement. Let's check out. In our last video, we have already discussed about the air movement through buildings. Today in this video, we will talk about airflow through buildings. On the basis of certain experiments, observations, some following factors can be isolated which affect the indoor airflow, both patterns and velocities. Basically, we have 6 major factors which governs your airflow through buildings. First is your orientation. Second is your external feature. Third is cross ventilation. Fourth is position of opening. Fifth, size of opening. Sixth, control of openings. Let's come to the first point, that is orientation. When we say orientation, it clearly means that the placing of a building. As we all know, the greater pressure on the windward side of a building is generated when elevation is at the right angle to the wind direction. So it seems to be obvious that greatest indoor air velocity will be achieved in this case. A wind incidence of 45 degrees would reduce the pressure by 50%. Thus, the designer must ascertain the prevailing wind direction from wind frequency charts of windroses and must orient his building in such a way that the larger openings are facing the wind direction. However, it has been found by Givoni that wind incidence of 45 degrees would increase the average indoor air velocity and would provide a better distribution of indoor air movement. On the right hand side, you can check out 2 pictures. Basically, in these 2 pictures, we have shown you the plan of a building. In the first picture, that is figure A, you can see a square-shaped plan of a building. Whereas, in case of figure B, the shape of a building is more like of a rhombus. Basically, the difference between the 2 figures is that the orientation of the building. In case of figure A, the orientation is 90 degrees. Whereas in case of figure B, the orientation is 45 degrees. Figure A shows the outline of airflow at 90 degrees and figure B at 45 degrees to a building square in plan. In the second case, a greater velocity is created along the windward faces. Therefore, the wind shadow will be much broader. The negative pressure, that is the suction effect, will be increased and an increased indoor airflow will result. The size of the outlet opening was not varied in this experiment. It was fixed at the maximum possible so that the suction forces had full effect. It is justified to postulate that with smaller outlet opening, this effect would be reduced, if not reversed. Basically, what we need to take care is, in case of your windward direction, the wind pressure will be more. If we are considering figure A, where we have placed the building in 90 degrees, wind will create pressure on the flat wall of the building. Whereas in case of figure B, the wind will be getting deviated because of the change in the orientation and angle created. It will deviate the direction of the wind. Whereas this shows the pressure of the wind would be more in case of figure A in comparison to figure B. It often happens that the optimum solar orientation and optimum orientation for wind do not coincide. In equatorial region or north-south orientation would be preferable for sun exclusion, but most often the wind is predominantly easterly. The usefulness of above finding is obvious for such a situation. It may resolve the contradictory requirements. First is your massing and orientation for cooling. Massing and orientation are important design factors to consider for passive cooling, specifically natural ventilation. As a general rule, thin tall building will encourage natural ventilation and utilize prevailing winds, cross ventilation and stack effect. Next is your massing strategies for passive cooling. Thinner buildings increase the ratio of surface area to volume. This will make utilizing natural ventilation for passive cooling easy. Conversely, a deep floor plan will make natural ventilation difficult, especially getting air into the core of the building, and may require mechanical ventilation. Tall buildings also increase the effectiveness of natural ventilation because wind speeds are faster at greater heights. This improves not only cross ventilation but also stack effect ventilation. Here in this case you can compare the amount of solar radiation so as your wind effect. In the first picture the building is one-story building, whereas in the second picture it is a tall building. Tall buildings improve natural ventilation and in lower latitude reduce sun exposure, while thin and tall buildings can improve the effectiveness of natural ventilation to cool buildings. They also increase the exposed area for heat transfer through building envelope. When planning urban centers, specifically in heating-dominated climate, having the building gradually increase in height will minimize high-speed wind at the pedestrian level, which can influence thermal comfort. The height difference between the neighboring buildings should not exceed 100%. Next comes your external features. When we say external features, it can be a fence, it can be a boundary of a building, it can be a tree, it can be anything placed externally outside the building in order to control your airflow. Wind shadows created by obstructions upwind should be avoided in positioning the building on the side and in positioning the opening in the building. External features of the building itself can strongly influence the pressure built up. For example, if the airflow is at 45 degrees to an elevation, a wing wall at the downwind end or a projecting wing of an L-shaped building can more than double the positive pressure created. A similar funneling effect can be created by upward projecting eaves. Any extension of the elevational area facing the wind will increase the pressure built up. Here in the picture on the right hand side, you can check out the prevailing wind direction inside the building structure can redirect prevailing winds to cross ventilation. If a gap between a building is closed by a solid wall, a similar effect will be produced. The air velocity between the freestanding trunk of trees with large crowns can be increased quite substantially due to similar reasons. These are basically meant in order to control the pressure of the wind. The opposite of the above means will produce a reduction of pressure. If a wing wall or a projecting wing of an L-shaped building in upwind from the opening considered, the opposite of the above means will produce a reduction of pressures. If a wing wall or a projecting wing of an L-shaped building is upwind from the opening considered, the pressure is reduced or even a negative pressure may be created in front of the window. Wing walls. Now the point is, what do you understand by wing walls? Wing walls are project outward next to a window so that even a slight breeze against the wall creates a high pressure zone on one side and low on the other. The pressure differential draws outdoor air in through one open window and out the adjacent one. Wing walls are especially effective on sites with low outdoor air velocity and variable wind directions. Here you can check out 12 pictures below. All are having different kind of openings so as the wind directions. In the first picture you can see this is a U-shaped structure. This particular thing is known as wing wall to deviate the direction of the wind. In the sense it will get inside the proper circulation, the wind will get inside after proper circulation of air will again come out from the same direction and carry on. So as here, but the shape of the wing wall is always different. This is U-shaped, this is of your T-shaped or L-shaped. This here you can see you have two notches kind of thing, proper circulation of air throughout. Eventually you can see in the first row you have one-sided openings, whereas in case of your second row you can figure out you have openings on both the walls so as to have a proper circulation. Now this variation continues in the third row as well, but you can see the positioning. When the position is very near, in this case the position is quite near and the wind direction is in an angular form. In this case, when the wing wall is in this form, it is not very convenient and the circulation is not being proper. Whereas in the last two, you can see we are not having proper amount of circulation. It is all because of the wrong placement of wing wall. So guys, what you need to understand is, you need to understand if at all you are providing the wing walls, you need to consider two things. First, the movement of the air. Second is the direction of the air. So as the positioning of your wing walls so that you can welcome wind and they can have a proper circulation throughout. So in this case, the first row is having a proper orientation, proper circulation of wind throughout the building. So wing wall is being considered as the external features. What we concluded out of this is there are 4 to 5 things which we can implement in case of your external features. For example, wing wall can be your external feature, tall trees with large crowns can be your external features, some fences, some kind of boundaries can also play as your external features. These have the capacity to control the wind pressure, whereas being a proper flow of wind into the building, whereas considering the proper circulation within in order to have thermal comfort. Next, cross ventilation. When placing ventilators for ventilation opening, inlets and outlets are placed to optimize the path air flows through the building. Windows or vents placed on opposite sides of the building give natural breezes a pathway through the structure. This is called cross ventilation. Cross ventilation is generally the most effective form of wind ventilation. Here you can see we have 5 pictures. First is your single opening, second is your two opening on the same wall, third is 2 opening with wings, fourth 2 opening with adjacent walls, 2 opening in opposite walls. Here we should understand how this exactly works. In case of a single opening, the air enters the building, rotates around and then come out through the same direction. Whereas in case of your 2 opening same wall, the air is getting inside through a particular direction and circulation without undergoing any cross circulation. It is having a thorough flow on the opposite direction and goes out. Whereas in case of your 2 opening with wing walls, you can see it is able to deviate wind in a very proper manner in comparison to the first one. The circulation is quite similar to the second wall. Next is your 2 opening on the adjacent wall. This circulation is quite preferable as it gets inside the room through a single opening, whereas after a proper circulation inside goes out through the different opening. This in short changes the direction of the wind, right? Whereas when we are considering the last case, it is the opening on the opposite walls. This is through and through cross ventilation of air. In this case, the corners of the room and some parts of the rooms are being prohibited to have a proper air circulation. It is generally best not to place opening exactly across from each other in a space. While this does gives effective ventilation, it can cause some part of the room to be well cooled and ventilated while other part are not. Placing openings cross from but not directly opposite each other causes the room air to mix, better distributing the cool and fresh air. Also, cross ventilation can be increased by having larger opening on the leeward faces of the building than the windward faces and placing inlets at higher pressure zones and outlets at lower pressure zones. In this plan, you can see different amount of ventilations and air mixing with different window openings. In the first plan, you can see in this particular area, we do not have any kind of ventilations. And this particular area is a stagnant corner because there is no airflow. Whereas in this case, you can see 2 windows over here. This is preferred as good ventilation. Whereas in this good ventilation, you again have some stagnant corners because the air is not able to reach this particular zones. Both the pictures are quite similar, and in this picture you can understand how we are having a mixing of wind. We have 3 openings on this wall through which we are able to get fresh air, whereas we do not have much of the cross ventilation over here, as this 3 walls does not have any kind of ventilation, or this particular room is also not having any kind of ventilation, because of which hot air is being created over here. Overall, if at all we are taking this plan, then we are having mixing of wind. In the sense, cold air is mixed along with the hot air. So as an architect, we should try our level best to have a cross ventilation while designing a building. Placing inlets low in the room and outlet high in the room can cool spaces more effectively because they leverage the natural convection of air. Cooler air sinks lower while hot air rises. Therefore, locating the opening down low helps push cooler air through the space, while locating the exhaust up high helps pull warmer air out of the space. This strategy is covered more on the stack ventilation. Here in this picture, you can check out high opening, low opening, and high and low opening. This particular thing has been properly explained in the 3 pictures below. Following figures, in the absence of an outlet opening or with a full partition, there can be no effective air movement through a building, even in case of strong winds. With a windward opening and no outlet, a pressure similar to that in front of the building will be built up indoors. This can make conditions even worse, increasing discomfort. In some cases, oscillating pressure changes known as buffeting can also occur. The latter may also be produced by an opening on the leeward side only, with no inlet. Here you can compare both the pictures. In the first picture, though you can see the distance between the 2 walls or the width of the room is more. So if at all we are having one opening on the single wall, one opening at the single wall, then the airflow would be somewhat like this. It doesn't enter to the end part of this particular room and circulates there itself. Taking a smaller turn, the air moves out. Whereas in the second picture, you can see you have a partition wall in between, which is obstructing this air to flow to the next air. But in this case, in the first case, the circulation would be better, though they have a single opening, because the air is able to circulate properly because of the less width of the room. Whereas in the second partition, you can see the air is not able to get inside because the opening is at the leeward direction. In both the cases, if the velocity of the wind increases or pressure of the wind increases, then also they are not able to provide a proper ventilation because of the distance and of the single opening. This is known as lack of cross ventilation. Next comes positioning of opening. The relative magnitude of pressure built up in front of the solid areas of the elevation, which in turn depends on the size and position of the opening, will in fact govern the direction of the indoor air stream, and this will be independent of the outlet opening position. The figure below shows that a larger solid surface creates a larger pressure built up, and this pushes the air stream in an opposite direction, both in plan as well as in section. As a result of this, in 2-story building, the airflow on the ground floor may be satisfactory, but not on the upper floor. It may be directed against the ceiling. One possible remedy is an increased roof parapet wall. Next comes your size of the opening. Windows or louvers should be 20% or more than of the floor area, with the area of inlet opening roughly matching the area of outlets. However, to increase cooling effectiveness, a smaller inlet can be paired with a larger outlet opening. With this configuration, inlet air can have a higher velocity. Because the same amount of air must pass through both the bigger and smaller opening in the same period of time, it must pass through smaller opening more quickly. Air flows from the areas of high pressure to low pressure. Anything that changes the air path will impede its flow, causing slightly higher air pressure on the windward side of the building and negative pressure on the leeward side. Here below, you can check out the 3 figures. First is your single-sided ventilation, second is your stack ventilation, third is your cross ventilation. Out of this, you can make out how your size of the opening makes difference in your design. To equalize this pressure, outside air will enter any windward opening and be drawn out the leeward opening. Because of pressure differences at different altitude, this impedance of airflow is significantly higher if the air is forced to move upward or downward to navigate a barrier without any corresponding increase or decrease in temperature. Here in this picture you can check out, this is the office where many people are sitting with the systems. The size of the opening through which the air is being entered is smaller in comparative to the opening on the opposite direction. It is because to control the wind on the windward side so as maintaining a proper circulation inside. Pairing a large outlet with a small inlet increases incoming wind speed. Next is your Venturi effect. Venturi effect is the reduction of fluid pressure when airflow is channelized through a narrow passage with at least 5-story high building that create high intensified wind speeds. This basically depends upon passive cooling of building, wind-induced natural ventilation. When air pressure is relatively low at the passage, there occurs such an effect from the building towards the passage. It is due to the effect sometimes the doors of the building do not open, and it is known as difficult doors. In case of skyscrapers, a constant flow of wind becomes constricted when forced through space between buildings, hence producing a strong flow beneath the structure. Next comes your control of opening. Sashes, canopies, louvers and other elements are the controlling of the opening. Also influence the indoor air pattern. Sashes can divert. Sashes can divert the airflow upward. Only a casement or reversible pivot sash will channel it. On the right hand side, the first picture is your sashes or the sashes. Canopies can eliminate the effect of pressure built up above the wind. Thus, the pressure below the wind will direct the airflow upward. A gap left between the building face and the canopy would ensure a downward pressure, thus a flow directed into a leaving zone. Next comes your louvers and shading devices. The position of blades in a slightly upward position would still channel the flow into the leaving zone, that is up to 20 degrees upward from the horizon. Fly screens or mosquito nets are an absolute necessity not only in malaria infested areas but also if any kind of lamp is used indoor at night. Without it, thousands of insects would gather around the lamp. Such screens and nets are sustainably reduce the airflow. A cotton net can give a reduction of 70% in air velocity. A smooth nylon net is better, with a reduction factor of only approximately 35%. The reduction is greater with higher wind velocity and is also increased with the angle of incidence. Next comes your windrose diagram. It is basically a graphical presentation in a circular format. The modern windrow shows the frequency of wind blowing from a particular direction over a specified period. The length of each spoke around the circle is related to the frequency that the wind blows from a particular direction per unit time. And basically the wind speed is measured by meter per second. Here you can see we have standard windrows diagram and we have speed range windrows diagram. So let's check out how will we graphically represent the wind direction as well as the wind speed by using windrows diagram. Here in this picture you can see this is a windrows diagram. Here we are about to plot windrows diagram. The first and foremost thing that we need to do is, while plotting windrows diagram, the first and foremost thing that we need to do is need to write down the direction first, that is north and south. From north we are starting 0 degree, 30 degrees, 60 degree, 90 degree. Gradually, eventually we are reaching again north with 360 degree, right? The next thing, these degrees are basically the direction of the wind. Next comes, now these concentric circles. The difference between these concentric circles are 5. This particular thing 0, 5, 10, 15, 25, 20, 25 are the number of measurement of speed. These are basically the speed of the wind. Next, here you can see in between 0 degree to 90 degree, I have plotted 30 degree and 60 degree. In every 90 degree span, I have plotted the intermediates. Hope this is probably clear to all of you. On the right hand side, you can check we have a tabular format. Here we have mentioned we have been given with some direction and number of measurement. The line representing the directions are known as spokes of Windrow's diagram. And the concentric circles are the measurement of speed of wind. The first thing that we need to plot is the direction is 0, 0, 0 to 0 to 9. This is the way we are supposed to, 0, 0, 0 to 0 to 9. This is basically 29 degree. This is basically 29 degree and the measurement over here is 5. So here we will see where is our 29 degree. 29 degree would be definitely before this 30, isn't it? Let's consider this as your 29 degree. And now the next measurement speed is 5. So this concentric circle is 5. So this particular area, this particular triangle angle created over here would be plotted as your first angle, right? So what we will do, we will hatch this particular area. Is it clear to all? Here it is 29 degree and so as the speed is 5. Hence this is the patch which we need to plot over here, right? Next example is your 030 to 059. That is, the direction is in between 30 degree to 59 degree. This is our 30 degree and this is our 59 degree, right? Now what is the speed? The speed is 14. Another thing that you need to keep in your mind is like you need to first check out what is the maximum speed given to you. If it is 14, then we can also plot the graph till 15 because our work would be done in between that, right? If at all this would have been 25 or 30, then we should have to plot the concentric circle. We have to plot the concentric circle till 30 or 40, right? This will totally base on the measurement, the highest measurement. So here what we have noted is, already noted is the speed is 14. Now what is the speed? This particular thing is your speed. The concentric circles are the speed. So when we are talking about 14, almost this is coming in between 15 to 10, 14, right? So I'll again take let's consider this circle as your 14. Hope this is pretty clear to you. Now this has been done and dotted in a dotted line. Yes, another thing that you need to do is, for example, if this is 29, you need to trim this angle, right? After plotting this, you are supposed to trim this. Like this was at 29, so after plotting this, you will trim it. And you can write 29 over here as well, and you can also write it here. Both the way it is correct. So next was your 59 and the speed is 14 degree. So this is basically 14. I'll write over here 14. Kindly don't get confused. This particular line is your 14. This line is a 14 and your degree was between 30 to 60, 59. So this is the, we'll trim over here. And it was 59. So I'll trim here as well. Now you're supposed to delete the extra part. Hope things are pretty clear with you. And you will delete the in-between part as well. And what you need to do is hatch. Correct? Hope you all have understood it pretty well. Hope it is clear to you all. Hope this is clear to you all. Next, I am not going to plot. This would be your homework. You can plot it in a paper and show it to me just for a practice. So hope everything is clear by now. If at all you develop any kind of doubt, you can call me up and we can discuss over it. So next is here, there are some twisted icons, global twisted icons, international buildings which have intentionally changed the shape in order to cut or reduce the pressure of the wind. So you can go through this. Next, this is some questions for you which you are supposed to practice after understanding module 3 part 1 and 2. This is totally based on part 1 and part 2. If at all you have any kind of queries or doubts, you can definitely give me a call. Thank you.